张洪江博士，北京致远人工智能研究院理事长，国际多媒体和人工智能研究领域的领军科学家。由于在多媒体研究领域开拓性贡献，他荣获2010年 AAAI 技术成就奖，2012年 ACM 多媒体技术成就奖。因其在研发和技术转换方面的杰出贡献，2008被授予美国杰出亚裔工程师奖。他已发表近400篇学术论文，拥有近200项国际专利，是中国大陆计算机领域 H-Index 影响因子最高的科学家。2011年，他加入金山，任集团执行董事及 CEO， 兼任金山云的首席执行官以及猎豹移动、迅雷及世纪互联的董事。2016年12月从金山退休，之后加盟源码资本任投资合伙人。张洪江博士曾担任微软亚太研发集团首席技术官及微软亚洲工程院院长，微软第一批10位杰出科学家，微软亚洲研究院创始人之一，并任副院长。2018年11月起，他担任北京致远人工智能研究院理事长。John Hopcroft， 约翰·霍普克罗夫特是美国国家科学院、工程院、艺术与科学院院士，曾任美国总统国家科学委员会成员，现为康奈尔大学教授。他是图灵奖、冯诺依曼奖获得者。他的研究领域是理论计算机科学。他将计算机科学萌芽阶段的零散结果总结为具有整体性的系统知识，提出用渐进分析作为衡量算法性能的主要指标，成为当今计算机科学的一大支柱。他在算法设计方面的著作《计算机算法设计与分析》和《形式语言及其与自动化的关系》成为计算机科学的经典教材，深刻影响了计算机科学工作者对算法的理解和应用。他近年来致力于推进中国计算机科学人才教育发展与改革。2016年，他荣获我国为在中国现代化建设中做出突出贡献的外国专家所颁发的最高荣誉——中国政府友谊奖。Bart Selman， 美国人工智能协会 AAAI 后任主席，康奈尔大学计算机系教授， ACM AAAI Fellow 斯隆奖获得者。Bart Selman 早年在戴尔夫特理工大学获得物理学学士学位，并在多伦多大学获得硕士和博士学位。他曾先后发表上百篇学术论文，其中获得6次学术顶会最佳论文奖，2篇经典论文奖，其论文多次发表在《自然》《科学》等著名期刊。作为人工智能知识表示领域的专家，他致力于将人类世界的真实知识表达成计算机可以理解并执行的内容。在2019年，由他领导制作并发布的《未来20年美国 AI 研究社区路线图》白皮书，为人工智能未来发展提供了重要指导。
我们2位对话教授的介绍视频。我想在这里再强调一次，其实Professor Hopcroft 也是我们智源人工智能研究院学术顾问委员会的委员。 Selman 教授也是这个Association for Advance in AI， 也就是 AAAI 的后任主席，也是这个人工智能领域的老兵，是这个美国未来20年 AI 发展途径报告的2位组织者之一。我想我们今天非常非常幸运，请到了这个图灵奖的获得者Hopcroft 教授和我们非常有经验也有远见的这个Selman 教授。那么今天我希望和2位这个教授和大家一起来回顾一下人工智能过去几十年的发展，并且呢介绍一下他们对于人工智能未来发展的方向和途径的看法。今天我们的题目或者我们的大会的主题叫做这个人工智能的新的10年。那么我想在我们谈新的10年之前的话，我们先看一下对于过去10年的回顾。Good morning, Professor Hopcroft and Professor Selman. Well, thank you again for joining me from Ithaca, New York, in this fireside chat. Although this is pretty early for a Sunday morning, so very, very warm welcome and thank you for both of you. As you know, the theme of this year's BAAI conference is the next decade of artificial intelligence. However, before we look into the next decade, I would really like to ask you to share your views on how AI research have advanced in the past 60 years, in particular, past 10 years. Professor Selman, how did AI actually evolve or develop in the last 60 years, in particular, last 10 years? I really like to hear your thought on this.
Okay, yeah, thank you so much. Thank you for having me at the conference. AI has started actually in 1956 with the first AI meeting. The term artificial intelligence was coined by John McCarthy. Formerly, he was at Stanford University. And I would say the initial work in the field was mainly by researchers interested in understanding the human brain and understanding thinking and cognition. So there was a lot of optimism in the early years of AI, but the problem turned out to be way, way harder than anybody had anticipated 60 years ago. I would say the field stayed purely as an academic discipline for many decades because we couldn't quite get performance anywhere comparable to humans. I would say the first sense that there was a change was probably when IBM built Deep Blue, which was in 1997. So that's a little over 20 years ago, built the first program to defeat a human in chess, and that was Kasparov at the time. And that was a breakthrough that was not really, was somewhat of a surprise at the time, and then brought people's attention to AI. And there were a few more breakthroughs like that. I would say the first self-driving car, which was a prototype in 2005, built by Stanley, Sebastian Turing at Stanford, showed self-driving capabilities in a limited context. So we started to see some examples of where the intelligent machines or AI applications started to match human performance on very restricted but still impressive tasks. I would say the big change, and that's why we're probably having this meeting, was in 2012 or around 2012 when deep learning was introduced. Now, you have to be careful that deep learning actually, I knew Professor Jeff Hinton, for example, one of the founders of deep learning from his days at Toronto University, mid-80s. The ideas behind deep learning have been around for decades. At least initial ideas of how to get neural networks to learn. However, the field had lost its steam, I would say, around the year 2000 and even up to about 2005. because it wasn't really showing the promise that one had hoped. However, around 2012, with enough compute power and enough data, a combination of compute power and data, GPUs, for example, to train deep networks, deep neural networks, multi-layered neural networks, changed the whole field by showing we could do things like computer vision and speech recognition. And that was a big surprise to everybody in the field, except maybe for 5 or 10 people who were working on it at the time. That really transformed the field. Machine learning was already popular, but had not had quite the impact one would think. But very quickly it was discovered that deep learning also outperformed all existing machine learning algorithms pretty much across the board. We see it in natural language, we see it in machine translation, we see it in all kinds of areas where people apply the deep learning methods and find it to be an extremely powerful learning method from data, if you have enough data. So that's what transformed the field in around 2012. I like to say what happened is that perception became doable for machines. I wouldn't say completely solved, but close to solved. And so that means that computers can see us, can see the world, perceive the world, can take verbal input, the speech recognition. So the machines are becoming part of our perceptual world. And now this can build, and that's the current excitement, can build on a whole range of existing AI technology, including decision theory, planning, reasoning. You can now couple that to the perceptual systems that deep learning brings, and that's leading to the enormous acceleration in our field. I would say for a scientific discipline, I've talked to physicists and people in other areas. It's very rare to have a transformation like that in any kind of scientific discipline, but AI was lucky to have such a transformation, and that's why we're here now. Okay, thank you. Yeah.
Well, thank you, Professor Selman. Professor Hopcroft, would you like to expand a little bit on how AI developed based on what Professor Simon has just, briefly mentioned?
Yeah, what I might do is say a little bit about what happened in the early 60s, because I got my degree, I was a PhD student from 1961 to 64. And at that time, there was basically nothing in AI. There was the work of McCullough and Pitts, who developed the threshold logic unit back in 1943, basically as a model of the nerve net in the brain. But it wasn't until 1960 that Frank Rosenblatt, who was at Cornell, actually trained the weights of the threshold logic unit to try to do something. And by the time I got my PhD in 1964, we only could train a single weight. And the reason for that was we simply lacked the computing power to do anything more significant. The other difficulty, which was holding AI back, was the lack of large data sets. The NIST data set of handwritten characters simply didn't exist. And in fact, when I was getting my PhD, I thought of making such a data set. I made a 10 by 10 grid and would write a character. And I was thinking of maybe making 1,000 characters, which is tiny by today's data sets, but by then would have been enormous. But the reason I couldn't do it is we simply didn't have the technology to scan the characters after I wrote them. And so one of the things for a field to develop, it requires a certain amount of technology, and these things go together. But back in at that time, John McCarthy created the Stanford Artificial Intelligence Laboratory called SAIL. And there were a large number of highly qualified researchers in SAIL. But they were working primarily on logic, and not too much really came out of it. And as Bart said, it wasn't until 2012 that when AlexNet came along. And it actually came about because of the ImageNet competition. The way you would enter this competition is you would be given 50,000 images. Each image would be labeled either a cat, dog, house, tree, what it was. And you would train your algorithm to correctly classify these images. And then you would submit your algorithm to the competition, where it would be tested on 10,000 new images which you had not seen. And the reason 2012 was so important is up until then, the error rate was about 25%. But with AlexNet, it dropped to 15%. And this was such a great improvement that people applied this technology in many areas, and it seemed to work. People don't know why it works, but it works. And it subsequently has been improved. AlexNet had about 8 levels of gates. But in 2015, the winner, ResNet, had 1,000 levels, and it had reduced the error rate to 3.6%. A human who looks at these images has an error rate of about 5%. One of the things you might question is, how do you train a network which has 1,000 levels of gates? Because the way these networks are trained is you create an error function and you take the derivative of the error function with respect to the weights. This is called gradient descent. But you can imagine taking the derivative of something which is 1,000 levels deep. But what they did in ResNet is they randomly filtered out most of the levels at each level, and you would train with only 7 or 8 levels for one round. Then you would pick a different set of levels and train for another round. But as Bart said, this technology has been used in many areas, in medicine, business, agriculture, finance, and it just seems to outperform the previous algorithms that were there.
Thank you, John. And I actually like to come back a little bit. You both John and also Bart, you both talk about the last in the last 60 years, and then you quickly jump into the last 10 years. Talk about the breakthroughs in deep learning. That you attribute that success to big data, to computation power, to new algorithm development. One thing I in particular interested in, and I would like to ask Professor Selman, because you have been working on the various classic AI problems like efficient reasoning procedures, planning knowledge representation, and even go beyond the connection between computer science and statistical physics. All those classic AI approach. My question is, why we haven't seen a breakthrough there, and why we have we are jumping into something we saw that already failed in early 90s, because that's a neural network, right? And for whatever reasons, and now we clearly know it was because we didn't have enough computational power. We didn't have enough data. But now, in the past 10 years, we see a tremendous progress, tremendous breakthrough. But where are we today in reasoning, in planning all those classic AI approaches?
Yeah, so that's a very good question. I think one has to be careful, because nowadays, indeed, deep learning is often equated with AI, or AI is equated with deep learning. The developments in the other fields, and I take reasoning, for example, which I've worked on a lot. So inference, computational automated reasoning. There actually has been significant advances over the last 2 decades. The applications are a little bit more hidden. For example, in my own area, the automated reasoning, they are very widely applied in a field called software and hardware verification. So a lot of Intel and big chip companies and software companies have their hardware and software verification groups, and they use that reasoning technology. So those techniques are actually being applied. Now, they're not widely known because you would have to explain what verification is or why it's relevant. But for the communities that work on things like verification or program synthesis, these techniques are widely used. Actually, I would say at some point I looked, it was about 10 years ago, whatever, where were compute cycles being spent? Well, at Intel and Microsoft, it was partly being spent on verification software running automated reasoning programs. So these techniques have found some applications, but much less widely known. In mathematical discovery, some open theorems, Robin's conjecture, recently Erdős discrepancy theorem, at least for discrepancy of 2, were proven with automated reasoning programs. So that's the first thing I want to stress, is that we may not realize it. It's not just deep learning or advances. I think probably the next very important example is AlphaGo. So AlphaGo, which sort of brought AI's attention in China, but worldwide really. It's often, AlphaGo is presented as a deep learning success and reinforcement learning success, but essential to AlphaGo is the Monte Carlo tree search algorithm. And the Monte Carlo tree search algorithm is really, one of those classical AI algorithms that actually was discovered around 2006, so it's not even that old, but it is a purely symbolic reasoning algorithm. And that's actually where I see the largest progress in some areas now, where we combine known methods from AI, search and reasoning and planning, with deep learning methods. Now, when these methods are brought to the press, for example, when DeepMind brought out their AlphaGo, they would not stress the use of Monte Carlo tree search. It's somewhat technical, but in a very interesting situation, Facebook at the same time was trying to build the world's best Go playing program, and Facebook purely bet on the deep learning approach, and they actually sort of did decide not to use any traditional AI techniques, and they didn't make it. So Google was much more, or DeepMind was much more open in combining technologies. Same thing we see in self-driving cars. A self-driving car is, you could try to train a self-driving car end to end, from visual camera input to steering wheel response, but that's not how the future self-driving car will be developed. It will be, deep learning will be a part of it for the vision system, but the control system and a lot of route planning, all kinds of other aspects of the car will have more traditional AI technology. So we should keep that in mind, that although, and I think that's actually a mistake people make, is by thinking, and I see it in a lot of students nowadays, that they think that it will be pure deep learning. It's much more likely it's a hybrid, and AlphaGo is actually the prime example of that, hybrid of technology. Yeah.
Well, thank you very much, Professor Selman. And I'm glad that we do have tremendous progress in all other more classic AI approaches, AI research. You should mention quite a few the applications of those classical approaches. I'm really glad we have you point them out, and it seems that in the last 5 years in particular, the deep learning has stolen all the thunders, and when people talk about AI, people think, by default, people think about deep learning. That's all of AI, and AI is deep learning. But we know that, actually AI is a much broader field than just deep learning, and so I'm quite curious, Professor Hopcroft. You have in the last 50 years have done so much work in algorithms and in computing theory, and so would you like to share with us some of your thoughts on the theoretical contributions concerning AI, from algorithm point of view,
Right. Let me first just remark a little bit about deep learning, because today it's just such a big part of AI, but it's just one tool in the AI toolbox. And what deep learning really is pattern recognition in a high dimensional space. If you're looking at images, say you're looking at a bicycle, the deep learning will not tell you what the function of a bicycle is. And if you show it something that looks like a bicycle, but doesn't allow you to get on it and cycle over to the subway stop, it'll still classify it as a bicycle. So one of the things we probably have to do is take logic and add it to deep learning. One of the things that the deep learning can do is, if you show it a bicycle, it can take the parts of a bicycle apart. It can show you that it has a wheel, that it has a chain, that it has some pedals, a seat to sit on, and handlebars to steer it. And what you can do with these parts is you can add some logic, and you can say the pedals allow you, by the chain to the wheel, to have something that moves, and the handlebars give you something that you can steer. And the fact that there's a seat, it's something that can transport you. And by adding some logic, you might be able to deduce that the function of a bicycle is to transport someone from one position to another. But to talk a little bit about the theory, the single threshold logic unit can be trained by a very simple algorithm. You show it an image. If it misclassifies it, you change the weight vector by adding or subtracting the image. And if the set of images is linearly separable, then the threshold logic will do it. But if it's not linearly separable, then what you want to do is map your problem to a higher dimensional space where the problem is linearly separable. And one of the important things is that the fact that the way you train the threshold logic unit, you don't have to map your data to this higher dimensional space. You can actually run the algorithm in the original space, and that was the technology that built the support vector machine, which up until deep learning was one of the key things in AI. But I want to talk a little bit about the notion of overfitting, because what you're really trying to do in AI is, let's say you're trying to separate real email from spam email. And we'll define something called truth, which tells you which the emails are, which are real emails, and which ones are spam. And what you want to do is find a hypothesis where the symmetric difference between truth and the hypothesis is small. And if the training set is sufficiently large and you can reduce the symmetric difference to 0, then with high probability, your hypothesis will have a small symmetric difference with truth. But this result is only true for one hypothesis. And if what you're trying to do is select a hypothesis from a large set, then the fact that the symmetric difference will be small is no longer true. And this is the concept of overfitting. But one of the things I'd like to mention is the mathematics that I mentioned here is actually the same mathematics that can be applied in other situations. Suppose you had a large data set. Suppose I had a data set which told me the salary and the age of every person in China. And I wanted to ask questions like, how many people are there in a certain age group in a certain salary range? But I don't want to keep the whole data set because I want to put it on my iPhone. And I want to put many other data sets on my iPhone. So what I'd like to do is take a small sample of the data set and trust that the answer I would get, if I scaled it properly, would be very close to the true answer. Now, it turns out that whether that's true or not depends on the range of questions you're going to ask. And it turns out the mathematics, which tells you what size sample do you need, depends on how complex the questions are. And this is the same situation as overfitting. But if people are interested in this mathematics, I'd like to mention that I wrote a book with Avram Blum and Ravi Kannan. And in chapter 5 of this book, it has all of the mathematics that's needed. And if you want to get this book, the deal that we negotiated with Cambridge is we could put the PDF of the book on our website, and anybody who wants the book can download it for free. So if anybody is interested in downloading it, if they go to my website and look underneath my picture, and where it says Cambridge, if they click on that, they will get the PDF. And the reason we actually negotiated that we could give the book away free, the PDF free, is that's one of the ways to increase your reputation. Rather than trying to maximize the money you'll get from the book, instead try to maximize your reputation. And so we negotiated this deal with Cambridge that anybody who goes to my website can download the book for free.
Thank you, Professor Hopcroft. Well, thank you for actually summarize the some of the deep learning issues and problems. I'm really impressed how you simply put all the issues in deep learning, especially using this general problem we often see, overfitting and data set issue. So I wonder, Professor Selman, do you have any more comments on deep learning and especially on its limitations? I know people have talked so much about deep learning. People, now it's like deep learning is everything. It works in almost every scenario, and so it's just very quick. 2 sentences. What do you like to say more about deep learning before we switch?
Yeah. So 2 sentences. So deep learning is very much a data-driven approach, and there is something in AI, traditional AI, that we call knowledge, and so there's a big difference, and so data is labeled images or example sentences, knowledge is something like Newton's law, laws about gravity. So human cognition uses a lot of real knowledge, and that's actually not so easily captured in deep learning. Now, deep learning is so effective, and we have data about lots of domains, but you can't tell a deep learning system about Newton's laws and have it do anything with it. So I think the big challenge ahead of it is, what's the next step in artificial intelligence? What is the next step we can model? And that will require things like capturing knowledge and reasoning.
Yes, Professor Selman, I would like to call that, what's the next step for our second half of our forum of fireside chat. And thank you both for your views on what happened in the last 60 years and what happened in the last 10 years especially for deep learning. And both of you have very, very deep background in computer theory and in classical AI. So you both mentioned the various limitations, various issues with deep learning, but that's in the past. That's all for the past. But let's look at the next decade. That's really the theme of our conference and this chat as well. So I would like to go first with Professor Selman. You actually is the incoming chairman of AAAI, and also you co-led the effort that come out with a new white paper on the 20 years of AI research roadmap for the U.S. We'll talk about 20 years, next 20 years of AI research roadmap for the U.S. and which was organized by Community Consortium. And so I really like you to spend a couple minutes to share with us what do you see as the future directions in AI and what the roadmap is focused on and where exactly are the research priorities.
Yeah, thank you. Yeah, so the roadmap was a community effort of AI researchers. We had about 100 leading AI researchers participate and provide input. At a very high at the highest level is the fact that the field is accelerating, AI is accelerating. We see a shift to larger research teams. If you look at what's happening in industry, if you look at for example, DeepMind, AI projects can now have 50 to 100 AI engineers or software developers on the project. So one of our recommendations was that the United States, we did this for the United States, invest in what we call a national AI infrastructure that would provide a test bed for different academic AI research groups to collaborate and to work on ambitious AI efforts. One example is what we call an AI-ready hospital, which would be a large hospital where people can develop and experiment with new AI technologies for healthcare. And another example would be a national lab for robotics or assisted living, where AI researchers from around the country could collaborate on new assistive technology using robotics and AI. These are efforts that are too large for individual academic groups. They require large investment in infrastructure, software development, robotics development, and so these have to be shared resources and would allow for collaborations. We stressed in our report that companies are, of course, making enormous investments. Facebook, Amazon, and China, of course, Tencent, and other big companies there are making enormous investment in AI technology, but they are driven by more commercial applications, and the focus is on commercial some financial incentives. For a country that may want to improve their healthcare system or may want to improve education, there are other objectives. So that's where government will play a role. Now, in terms of concrete technologies, it's all about integrating different technologies. So again, it's tempting to say, well, you just train an end-to-end system for your application and you're done, and that would be a deep learning approach. There's a general understanding that will not, in general not work. Partly will not work for things like safety. So if you have an end-to-end trained self-driving car, even if it would be driving reasonably well, it would be very hard to verify or to validate that the car drives safely. So that's it's much better to develop separate components and validate the separate components of the system. In healthcare, we train end-to-end systems, but if you give a medical image, an MRI, and you get a diagnosis, the medical doctor wants to know why is this diagnosis being made? What is the reason for it? What is the causal underlying model for it? And that comes back to this notion of knowledge. A human wants an explanation and needs an explanation, but an end-to-end deep learning system cannot provide that. So there has to be some integration between knowledge and what's learned by the deep net, so that it can communicate to the human user why certain decisions are made or certain solutions are proposed. So it's all about integrating technologies on a large scale.
Well, thank you, Professor Selman. I'd like to, follow up with one, priorities you mentioned in the 20 years roadmap. That is, self-aware learning. What exactly you mean by self-aware learning, and is why you think that is a high priority for the next 20 years of AI?
Yeah, so again, this is a great example of things we haven't solved yet. So human learning, if you think about when we go to school and learn new skills or a new scientific field, is a very different kind of learning than data-driven learning. So data-driven learning is giving hundreds of thousands of examples, and we learn from that. Humans often learn from one or two examples, and maybe some instruction on the side. Self-aware learning is people also can reflect on how they're learning and can reflect on are they improving or not. So we're talking about what's called lifelong learning, where we want the system to reflect on its progress on the learning, on the task, and then adjust its learning behavior to say, I don't quite understand this aspect of, let's say, you're learning calculus. I don't quite understand this aspect of calculus. I'm going to ask a question, or I'm going to do some exercises on that aspect of calculus to get better at it. So this reflection on its own learning process, using very few examples, one or two examples, or 10 examples, and not millions of examples. Those are kinds of learning styles that are unique to humans, but not captured with current AI. And the feeling is we have to, because that's how humans learn during their lifetime.
Yeah, very, very, very good point, Professor Selman. But then if we look back the history, for more than 50 years, the AI has, had a very slow progress. And then until 10 years ago, the deep learning hit the field, and then we see, boom, everything, seems to be solvable, by deep learning. So when we talk about, the next decade, we talk about this, self-aware learning. And do you think it's going to take us another 50 years to see any breakthrough? Or you see, in 10 years or 20 years, we are going to have something as big as deep learning?
I think it's more near term, so 10, 20 years. We have to, it's hard to predict because some of these things require fundamental breakthroughs. However, we're seeing some results on where people, and it's often using deep learning methods, but even learning, combining deep learning with symbolic approaches, There's still breakthroughs needed, but we see already progress in those areas. A big difference with the first 50 years is now we do have the data and we do have the machine power. So I'm quite optimistic that those new steps will be made.
Even when we talk about the self-aware learning, you still think that data and their computing power are the two most important factors that that differentiate from the past.
I would say so. Those are necessary components. I would say for self-aware learning and connections to knowledge and reasoning, new ideas are needed. It's not like that. So that, I mean, a confusion often is that, and that's of course especially for younger people entering the field is, deep learning is so successful, there are no other problems. But that's actually not really true. And if you look at something like machine translation, we can do very well. We can do up to about performance of 80-90% of human translation. The question is the last 10%, the last 5%, and that may require something totally different. So one thing we have to be careful is in a lot of applications doing quite well, financial modeling and advertising, and doing very well. You can be fine at 90%, but in many applications like self-driving cars, you have to be very sure and nearly 100% sure that the car is safe, not pretty sure. So that last 5-10% requires extra work.
Yeah, you mentioned it earlier, and now again you mentioned again. There is a huge difference between data and knowledge. We talk so much about the knowledge, and learning is more to do with knowledge. And this is great, but really, how do we go from data to knowledge? This is a huge gap. And so, Professor Hopcroft, would you like to expand a little bit, on the futures of AI in the next decade?
Okay, well, one of the things you asked this question is how soon will we make progress? And if you look back at history, you'll see that things are speeding up very fast. It took a long time for agriculture to develop, thousands of years. Manufacturing only took hundreds of years, and AI has only taken maybe 50 years to develop. So I think developments will come very, very quickly. It's just as you build up the tools and things to support what you're doing, you can work more efficiently. But Bart also mentioned things like humans want an explanation as to why a decision was made.
Yes.
And so there are a number of issues like this that we're going to have to resolve. And I might mention a few of them. The one about wanting to know how a decision was made, I guess that's called the black box problem. If for example, if I used AI to grade the undergraduate exams in my course, a student might ask the question, why was this problem marked wrong? And if AI doesn't tell me why it marked it wrong, only that it's wrong, the student's not going to be very happy. There are other things like bias. If we train a network using data which is biased, that bias is probably going to be captured in the algorithm. For example, if most high-level jobs today are held by men, and we ask an AI program to find a candidate for a high-level job, they'll probably select a man. So we have to figure out how to get bias out. And then, of course, there are unintended consequences. For example, if you ask an AI program, how do we eliminate the coronavirus? It might respond with, kill all humans. That's not exactly what you would like. Or if there's a street where a number of people are jaywalking and getting hurt, If you ask a human, how do you solve this problem? They'd probably say, put up a fence and prevent them from jaywalking. Whereas the AI program might say, remove the street. There's also the question of mistakes. If the self-driving car that I'm riding in is in an accident, who's responsible? I hope it's not me as a passenger. Is it the designer of the car, or is it the designer of the algorithm? And we're going to have to modify our legal systems to answer some of these questions. There's also the question of how do you keep learning? If you've trained the self-driving car, it'll handle most situations, but as it drives around, you'd like it to learn how to drive better, the same way a human would. Other issues, the percentage of the population that in the future is going to be needed to provide all the goods and services that we need is going to be very small. And we better address this problem. You don't want a large number of people sitting around doing nothing. How do you engage them in meaningful activity? AI also is going to generate a significant amount of wealth for countries. But one of the important questions is how is this wealth going to be distributed? If it only goes to the high-level people, you're going to have a very bad distribution of wealth in a country, and it could cause a riot. There's also the issue of social interaction. If we're dealing with computers rather than humans, what impact is that going to have on humans? And then one of the things is going to be the importance of education, because I think AI is going to eliminate a large number of low-level jobs. And if a person in the future wants to have a job, they better have a good education. And so education is very important. And that's one of the things that I think nations are going to have to focus on, is in improving education.
John, thank you very much. You listed a number of very important issues on how do we move forward in AI and what the social consequences, what the issues we have to address. And also, Professor Selman, I really like and appreciate you sharing with us on the research priorities which you outlined in the 20 years roadmap for a US AI community. And if you allow me to rephrase it, but I think what you refer in your research priorities are the three priorities. First one is that you instead of just talking about deep learning, we should focus on integrated intelligence. That's go beyond just deep learning. It's bridges data with knowledge, and also on meaningful interactions. And the last one we just talked about is self-aware learning. So those are the three priorities you outlined. And I want to switch gear a little bit and just to go with a couple of very straightforward questions. People are sometimes impatient. So in the next 10 years, will we be able to reach the human level AI, sometimes called artificial general intelligence, AGI?
Yes, artificial general intelligence. So my view is we'll see, so the next 10 years, I would think we will still be more on specialized capabilities. So, superhuman face recognition, superhuman image recognition, various somewhat narrow cognitive or human capabilities. But I could see 20 years, I'm hoping that we're going to see significant progress in 10 to 20 years on bringing these areas like common sense, knowledge, true natural language understanding, Some of these areas that need reasoning knowledge, I'm thinking like 10 to 20 years. I wouldn't say necessarily 10. A lot of excitement is, people focusing on what we're seeing now, on where things really work well. And of course, those are the things where we have tons of data. So I think the next 5 to 10 years we'll focus on those because they have the highest immediate payoff. Slightly longer road, and I'm thinking more 20 years, we'll get to the more human-like capabilities. And as soon, it's very simple. As soon as we have true natural language understanding, which means, the machines can read a book, the machines can read from the web and understand their reading. As soon as that's solved, and I'm not saying it's an easy problem, but when that's solved, then you get the next super acceleration, because then the machine will have all human knowledge and read every book there is to read. So now these books are viewed as data, sentences, bags of words. That's not enough. You need that understanding, but that understanding, as soon as we get that deeper understanding of natural language, there will be another acceleration where machines can use human knowledge, and then they will have general intelligence.
Well, John, do you have anything to add?
Well, yes. Most of the research that's being done today is what I would call applied research. People are focusing on specific problems and trying to improve them. So probably for the next 10 years, the advances will simply be sort of engineering advances, how to solve particular problems. But it's going to require basic research where someone just goes off and looks at something that they're curious about. And it might not even be AI. I should point out that there's been, in the last 25 years, significant research based on how the brain develops in a human. And people now know that in the first 2 years of a child's life, the brain learns how to learn. And so people now are thinking about stabilizing the life in inner cities for every child that's born. Because experiments where they did research of this type 25 years ago, and then they looked at what the impact would be 25 years later, there were fewer mental problems, higher educational levels, a number of things, and they realized that this could be one of the best investments you could make. So where the advance for AI comes from may not be computer science. It might be people who study, biology. And so it's just not clear where that advance will come from. But I think, as Bart said, in 20 years, there probably are going to be really significant advances.
Thank you. Well, time really goes fast. We almost used up our 1 hour time slot. But before we end, I'd like to pick up a couple of questions from the audience, and definitely people would like to learn a bit more from both of you. And in particular, Professor Selman is the incoming chairman of AAAI and also the co-lead of the report and initiative on the next 20 years of AI in the U.S. So one question is, could you talk a little bit on what the U.S. has done right or wrong in AI research in terms of policies? And I mean, in particular, funding policies. This is also a question I really, I'm interested in, being the chairman of the BAAI.
Yeah. So I think what the U.S. has done right is it has stuck with research investments in AI for 60 years. DARPA, that's actually a defense agency that has invested a lot in AI, but also the NSF, the National Science Foundation. But one motto that had at DARPA, fail fast and fail often. So they actually had repeated investments in AI over decades, even when nothing seemed to be working. And that's a very tough thing to do. But this comes back to a little bit what Professor Hopcroft says is, you don't necessarily know where the next advance is going to be from what corner. So, now and deep learning is a good example. We could decide all to just do deep learning. That's probably not where the next big breakthrough is going to come from, because you have to invest broadly in research. And that's one of the key things. You have to have a broad portfolio of projects. I would even stress that something like deep nets, it was almost, the field of neural network had almost died out. There were 5 or 10 researchers worldwide who still believed in neural nets around 2010. So that's a beautiful example of, if you keep investing in a diverse portfolio of research projects, you will hit the next breakthrough. If you limit your investment to certain favored areas, and especially areas that are favored at this moment, you will probably not hit the next research breakthrough, because research breakthroughs are revolutionary and not evolutionary. So I think that's what the US has done right. Now they're facing a challenge, because now I think AI, some AI for healthcare or for robotics or certain kinds of AI applications need to have a larger scale investment. Now the US has had those investments, for example, Human Genome Project, the Hubble Telescope, LIGO. So it has made some next level of investment in larger projects. I think AI is ready for that, and we hope that the future, we hope to convince the funding agency that that's the future of AI, larger scale, more collaborative AI research projects. And we're actually seeing some of those are starting. The first AI centers, research centers, are being formed as we speak in the US.
So let me turn the question a little bit around, what do you see China has done right in AI? And
so I think China is doing incredibly well in AI. If I had one piece of advice, don't look at the history of AI. There are a number of hard problems, and I didn't have quite enough time to go into things like common sense reasoning and those kinds of things. There are a number of very hard problems that we know from the history of AI that actually have not been solved. So I would encourage a new student in AI to be broader than the pure data-driven approaches. There's a certain limit you're going to reach there, and you want to get to more human-style learning, more one-example learning, 10-example learning, true natural language understanding. So I would encourage the new generation, I tell my own students that, to take a textbook like Russell and Norwick's textbook on AI and familiarize yourself with the history and the broadness of the field, so that you realize what is missing at this point. And there are some very important areas that are missing, and that's where the next breakthroughs will be. So be aware of that, even if you focus on deep learning. Don't become too narrow.
Great. So your advice is don't be too narrow. This is and also you feel that what US has done right in the past is really allow people to explore, allow research to explore, and allow project to fail fast, and perhaps even feel bigger, so you can learn from those failures. And so we're running out of time. One last question for both John and Bart, and for you both professors. And in one sentence, each one of you, in one sentence, what will be the advice you gave to Chinese AI researchers? This is actually a question from the audience.
Well, some of the advice I would give is move away from metrics. Chinese researchers are very interested in the number of papers they publish and the amount of research money they get. And it would be good for China to eliminate these metrics and get some other metrics which would be much more valuable.
Great point. So don't count the numbers. Don't just be counting. Great.
Right.
How about Professor Selman?
Yeah, I would say be creative and willing to do to take on research questions that other people are not considering. So again, I think it follows up a little bit on John's question. I see a lot of machine learning research, which is, I ran 100 benchmarks on 100 benchmarks, and I tested 20 different variations of an algorithm. That type of research leads to papers, and they can be counted. But I would encourage people to keep the bigger questions in mind and do something. Look at areas that are unsolved and are the hardest areas. Now, you have to have an infrastructure that allows that kind of research, but that's where the next breakthrough will be much more likely than the next incremental paper.
Well, thank you very much, Professor Selman and also Professor Hopcroft. Well, we have spent the last hour, to looking back what progress we have made, in particular the breakthroughs in deep learning and what the limitations of there are still there with deep learning, what we should do in the next decade and what we can expect for the next decade. And I really appreciate also your advice on what Chinese researchers should do and should consider. And we will take your advice, and hopefully we can build a new matrix system, or really eliminate all the existing matrix, and to encourage more brave, more exploratory research. So thank you very much. 好，各位听众，我看到大家有人问，就是在哪能找到这个Selman 教授他这个起草的这个美国今后20年的AI 的路径图。如果你在网上搜索那个Bart Selman， 你应该能找到那个报告。刚才 John 说的那本书，在他的那个网页上，如果你在他的那个照片底下去找的话，你也能找到那本书。好，再次感谢大家参加我们这次智源大会的这一次高峰对话。好，谢谢大家。